That which is written in the rocks is different from what was written by humans as history. It is not spun by rocks to satisfy an agenda. It's not written by a winner. As best she can, Dr. Thomas tells Montana history written in rock. It is the big story of life and evolution in what is now Montana. Rob is deeply passionate about family, mountain recreation, and international travel. As many of you know, he loves playing guitar around a campfire, especially at field camp. He cares deeply about science for the public good. You're in for a real treat tonight. Please join me in giving a warm welcome to Dr. Robert Thomas. All yours, Dad. Thank you.
All right. Can you guys hear me okay on this microphone? All right. A very kind introduction from John. I would add that my time at the university in Dillon, for those that are Montanans or been around Montana for a while, know that Western was the state's normal school. It was the state's teachers college, one of the original four founded in 1893. Montana State University in Missoula, Montana State College in Bozeman, the land grant, Montana School of Mines in Butte, and Montana State Normal School in Dillon. And why Dillon? Well, because it couldn't possibly, it was almost all women, and you couldn't send them to Butte. And there was a train line that went to Dillon. And Dillon was a safe ranch town, surrounded by debauchery in the mines in Virginia City and Bannock and other places, but not itself too scary. And they literally picked them up at the train depot in town and directly escorted them by wagons to the campus where they stayed. Because as much as Dillon might have a reputation of being this quaint ranch town, it was full of brothels and bars. Until fairly recently, and the bars are still there. So I got there in '93. I shouldn't go down this path, John. I've got a lot of history to get through here, but it's important to me to express this story about Western. I've got a Western graduate sitting right here in the audience, and there was no geology program, there was no history program. There was elementary, secondary, and early childhood education when I arrived in '93. It was the last normal school in America. And that happened mostly because it's isolated down in Dillon, and they had a policy of just don't tell people what you're doing and everything will be okay. That was all well and good until the state decided that headcount-based funding was going to be the way in which they funded the universities. And that happened in '93, the year I arrived. And that was the year everything changed. And a lot of people didn't realize it. But it was at that point, you had to be growing or you were dead. And so we went about building a liberal arts university, and I had always dreamed that we would, build a university that was, got students doing things, learning through experience. And the thing that hinders that from happening is time. If you're given 50 minutes a day, 3 days a week, you're going to lecture. That's the standard 3-credit class in America. So the only way to beat it is to teach one class at a time and have those students be yours for a month. And like all good ideas, we just flat stole it from Colorado College. I stole it. It was my idea. But you don't make anything work on your own. I floated this idea, people made it happen, and we fought an 11-year war in Dillon. You can imagine, if you know the state. There's a little bit of resistance to change down in southwest Beaverhead County is basically resistant to change. And I always viewed it as a positive that the community cared so much about a university that had been there since 1893 that they wanted to run the carpetbagger from San Francisco out of there on a rail. That'd be me. And the Dillon Tribune editor actually wrote a full paper on why I should leave. That was a little scary, but we survived it. So 20 years later, we've been at it, and I just last spring taught a class called Geology of Greece, and I took students to Greece for 2.5 weeks. Who else can do that? So Western is something different now. And part of the reason why I go around and do these talks is because I want people to know this. Western is different. And in my view, and I'm biased, Western is the way education should be. Because most of us don't learn well by memorizing and regurgitating information. I'm going to do it to you tonight, and I feel guilty about it. Because I know it's wrong. Because if I had you for 3 hours on an outcrop, I could get you to understand geology. This is going to be much harder. Right, John? Yeah, absolutely. So we learn by experience. I'll tell one story on it. Bill Tash, Senator Bill Tash from Dillon, Montana. And he was a Guinness, as they say. And I was at a talk like this and talking about it. Chancellors were all, too afraid to stand before the public and talk about it, so they would put me there. So I'm up talking about this, and I can see him nodding his head. So I get done with it, and there's a reporter in the room, Perry Backus from the Montana Standard at the time. Perry's a native the Backus family goes back to Armstead, which is underneath Clark Canyon Reservoir today, south of Dillon. They're old school Montanans. He can see this happening, and he comes over, and he says, "So, Senator Tash, what do you think about this block idea at Western?" "Well, I tell you," he says, "I was against it. But after I've been listening to what Rob has to say here, I'm starting to think that somebody is not telling me the truth, because this sounds pretty good." And I looked at Bill and I said, "Bill, you didn't give your kids 15 weeks of fence mending lectures before you put pins in their pockets and a hammer in their hand and you went out and fixed the fence. And then once you're out there fixing the fence, you talk about why the cows are being rotated from this pasture to that pasture and why you're doing this thing, and that's the theory being infused into the practice of the discipline itself." Instantly, he got it. And he was a champion for us in the face of a storm that lasted for 11 years, at least. It actually lasted for a good 15, because people fought against it for the next 5, hoping that they could scuttle it. So this is a story unto itself for another day. Because today what we're going to do is go through 4 billion years of Earth history. So let's start for some basics. All right, here's the bottom line. This planet was a molten ball in the nebular cloud that was our solar system. Okay? How do we know that? All right, John, you can't talk. Okay. We know it. What's that?
Meteorites.
Okay. You're on the right track. Meteorites are hugely important, but what we know from geophysics is that the Earth is differentiated with the heaviest elements towards the center and the lightest elements towards the outer parts. How do you get that if it's not liquid? Right? It has to have been liquid in order to be differentiated so that you have the heaviest elements towards the center of mass. Basic physics. So the Earth was molten. When it started to form a crust in the coolness of space, it differentiated that crust in two ways. It differentiated a heavy crust made of heavy elements and heavy minerals as a result that just happened to form dark rocks. Basalt, a rock that most of us have heard before, its name, okay? The rock of the ocean floors. And it also differentiated what I like to call the foam on the beer. The light elements, silicon and sodium and potassium and other light elements that formed light minerals that formed the light blobs of crust that are the continents. All right? But those continents in the beginning were nothing burgers. These were small quantities of continental material and vast quantities of oceanic material. Now, they have differential densities. The ocean floor rock is heavy. The continental rock is light. And that difference is so great that it's different. It's as great as water versus air. Okay? That's the density difference between the ocean and the continents. What's the lowest point on the Earth? The oceans. Right. Why? Because underneath them is a Play-Doh-like rock, a hot, mushy rock of the interior of the Earth that it sinks down in because it's heavier. Y'all with me? And the continental material floats up higher because it's lighter on that surface of mushy rock below. And that was true in the beginning, and it is true to this day. Everybody good? All right. That is crucial to start there, because you can't really understand anything of the rest of what we're talking about, I think, if you don't understand this basic differentiation that occurred right in the get-go. All right, now, these two different types of crust form plates, rafts, if you will, of rigid, brittle rock on the outer part of the Earth, moving around on that mushy layer down below. Everybody okay? All right. So there's South America separating from Africa on that mushy layer. And notice that the plates, here, I'll go back. Can I go back and do it again? I think I can. Notice that the plates are both, oh, I've got a pointer. They're both oceanic material and continental material. So here's the plate boundary, and here's the plate boundary. The plate is made up of both oceans and continents. All right? This is not continental drift. Many of you were taught continental drift in high school. Let me see a show of hands. See, ooh, drives me crazy. All right. Alfred Wegener came up with this great idea of continental drift, probably looking at ice and seeing how ice broke up, and then equating that to the fact that the outie of South America fits really well with the innie of Africa. I mean, mariners knew that continents had moved around on the planet from the minute they started making maps of the outlines of continents. It's just like, well, duh, they fit together, right? Anyone can see this. They must have been together. Wegener just proposed an idea he called continental drift, but he had several fatal flaws. One, to our historian, he was German. Two, he was German in 1919. And he came, and 3, he was not a geologist, and which it's pretty low when a geologist is looking down on somebody. I mean, the hierarchy is the physicists, okay, theoretical mathematicians looking down on the physicists, looking down on the chemists. You know, geologists are so down below. I mean, it's like below the sociologists, for Christ's sakes. And that's low. So Wegener was low on the totem pole, German, at a very bad time to be German. And then he made the fatal flaw of bringing this idea of the origin of continents and oceans, his book, to Texas to give the first talk in the Northern Hemisphere on this topic. Well, at least in North America. Okay? No offense to Texans, but they were interested in finding oil, even then. And they could not see how this stupid idea of moving continents around on the surface of the earth, and they'd all been back together into one supercontinent that he called Pangea, all lands, had anything to do with finding oil. John, does it have anything to do with finding oil? No. Everything. It has everything to do with finding oil, finding minerals. They just didn't know. So he got run out of town on a rail, and he fell into a crevasse in Greenland. You gotta love it. I mean, what a great story. So then, my academic great-grandfather, my advisor for my PhD was Jody Bourgeois, the only female in a department of 55 males at the University of Washington. Boy, did I learn something. And it wasn't, it was good for me. Bad for her. Her advisor was a guy by the name of Bob Dott, who was a famous historical geologist. He wrote the book that we all had in historical geology at Wisconsin. And Bob's advisor was this guy, Marshall Kay, who championed this idea called geosynclinal theory of mountain building, that mountains were built by piling sediment up in one spot that would then pooch the earth up in another and create mountains. It's like, oh, hold it a second. Don't you have to have a mountain first to create sediment, to load onto the crust, to pooch it down and make a mountain? Kind of a chicken and egg problem here. Right? But nobody really paid attention to that, and this geosynclinal theory kept going on, and Kay don't think for a nanosecond that politics don't play a role in success in science. He had the politics on his side. Wegener was doing well in death in the Southern Hemisphere. For some reason, the South Africans and the Australians and the South Americans were down with Wegener. I think probably because the data showed he was right. But Wegener did not understand that continents and oceans moved together. He kind of envisioned that the continents moved around by plowing through ocean floor, and that's not possible because continents are light and ocean floor is dense. You can't plow the foam through the beer. Make sense? All right, so Wegener, the rejection of continental drift happened for the right reasons. It was physically not possible the way he was proposing it. But he had every reason to be ignorant about the ocean floors because we didn't really know very much, right? The Brits had been, drilling the ocean floors, but we knew that there was a bunch of muck and that underneath that muck was basalt, and that's about all we knew, right? We didn't know in the early 1900s there were mountains on the ocean floors. When did we learn that? World War II. The Navy knew it for years. Proprietary information. And then they gave the sonar technology to Scripps, and Woods Hole, and they put graduate students out on the ships to get sick and remap it. And they're like, whoa, there's a huge mountain range in the North Atlantic. And the Navy was like, yeah, we know. We had to find that thing to find out where those U-boats were hanging out. So a plate is ocean and continent. Whoops, let's go back. And the boundaries of plates are where things happen. So where ocean floor splits apart, that's called a divergent plate boundary. There we go, divergent plate boundary. And where they collide with one another, that's called a convergent plate boundary. And ocean floor being denser than continent, it gets subducted, which just means that it gets pushed and pulled underneath the continent that it is colliding with, or with younger, more buoyant ocean floor, where you have ocean floor colliding with ocean floor. The Japanese islands are a good example of that. The Aleutian Islands are an example of that, where warmer ocean floor rides up above colder ocean floor and it sinks underneath it. You get chains of volcanoes that are island volcanoes, not Hawaiian style, that's different. Okay? And then those that are chains of volcanoes on land, like the Cascades, those occur from this subduction of ocean floor underneath continent. And they'll parallel that trench, that point of contact between the two plates, what's called the trench, on land. So the Cascades from Mount Lassen to Baker is paralleling that trench offshore. Make sense? All right. This will all come back because we're going to see evidence that these things happened in Montana in the past. All right? And then hotspots. I would normally leave hotspots out, but by God, we live north of one. And it just happens to be the largest explosive volcano on Earth. And if it goes off while I'm speaking, we're done. And I'll show you the evidence why. All right. Everybody good on the basics? So the bottom line, the planet is moving around. They're plates, and the plates spread apart, the plates collide with one another, the plates slide past one another, which is less of a big deal in Montana. There's one big sliding fault in Montana called the Lewis and Clark Line. I'm not even going to talk about it because we don't really know that much. It's an old fault, and the sliding is poorly understood, and it's not important to the story. So I'm going to skip it for those that are geos and are like, well, what about the Lewis and Clark Line? It's like, just not that interesting. Not in 4 billion years worth of interesting stuff. You got to make decisions. All right, so there we are. Montana has a history. It took out of the book the cross section from here to there. Okay, getting down to Gardner. We'll see that tomorrow, or some of that. We'll see all the elements of that, for the most part. And what's the point of that? The point of that to me is that, with a little bit of help, really, not, I'm not a bright guy. I can understand this. Geology's easy. You just need some basics, right? Think of it this way. You build a house. That's the earth forming its original crust. Everybody with me? All right. Then you're not a very clean person. So the dust starts to accumulate on the windowsill. And you decide, I'm just never cleaning that windowsill. Where's the oldest dust? Of course, at the bottom. And if that pile of dust has been altered somehow, crumpled, pushed up over younger dust, tectonics has happened. It's disrupted our dust pile. You got it? If the Earth were stagnant, we just have a dust pile. Okay? We don't have a dust pile. we actually wouldn't be here if it weren't for plate tectonics. But so start there. The oldest rocks are at the bottom of the stack. So in this picture, the oldest rocks are these brown rocks with the XAM here. That's called the basement because it's basically the vast majority of geological time. Rocks are like people. The older the rock, the more metamorphosed it is. Get the point? I mean, I'm feeling it on a daily basis that time is metamorphosing me just like it does with rocks. So when you go back into deep time, the rocks just have a higher probability of being screwed up, of being caught up in a collision of plates, to being buried deeply by other rocks, by having rocks shoved over the top of it, burying it even deeper and making it hotter and changing it. Make sense? So it's a probability issue. The older the rock is, the greater the probability it's gone through change in a rock. That means pressure and temperature, and it's going to be a metamorphic rock. Changed. All right, I'm a SED guy. I like trilobites, okay? I hate metamorphism. With a passion, I hate metamorphism. There's nothing worse than a good Cambrian limestone that's been screwed up by heat and pressure. And then some bloody minerals injected into it. Ruining my trilobites. All right. So the point is, the basement gets really hard to understand because it's old and it is metamorphosed. So what was it? That is a very hard thing to get at. We're using tricky techniques of geochemistry and geochronology to try to figure these things out, right? But I can take you to a sedimentary rock and I can point at it and I can say, look at that, there's a coral right there. And you'll look at it and go, that's a coral. And we all know that corals don't live in Montana. It really very little should live in Montana, but certainly not corals. And so you know that there was a tropical warm ocean there when you see that coral in that rock. But these metamorphic rocks, awful. So we call them the basement. And boy, does that make some of my friends that love metamorphic rocks mad. It's more than the basement. There's a story to be told, and there is. Here it is. All right. So the continent of North America is an assemblage of pieces of foam. Okay? Continent, the foamy rock, the light stuff. Why is it a collection of them? Because when they collide with one another, they're the same densities, and one doesn't subduct underneath the other. They suture against one another. I mean, there is a little subduction. This is 101. India colliding with Asia, right? India was a separate island, headed on its way towards Asia with a subducting ocean floor out in front of it. Then, ba-boom, it collided with India and raised the Himalayan mountains in the collision. And it sutured itself to Asia. Y'all with me? So the whole continent of North America is made up of fragments of different ages that are sutured together. And we live on that block that is called the Wyoming block, right there. One of many that makes up North America. And what you're looking at right there, that could be broken apart into untold numbers of pieces going forward into the future. I mean, humanity may not make it, but the plates are going to continue to move. Right? So that's going to bust up. That's going to bust up. It's busting up. It's called the Basin and Range. And we're part of it. That's what's happening to us right now. We're pulling apart. And you guys are on the eastern edge of it here in the Paradise Valley. Okay? So continents don't always stay, there's my point. Continents don't always stay the way we see them. So you look at Africa, that's only how it is today. It was once part of a supercontinent called Pangaea that Wegener coined. And it busted up into the continents that we see today, separated by oceans that formed new at that time. Make sense? As a result, ocean floor is young and continents are old because the continents don't get subducted. They just get moved around and they're eroded, but they get moved around and it's the ocean floors that gets recycled back into the interior of the earth. So the oldest ocean floor is a couple 100 million years old, and the oldest rock that we have on a continent is over 4 billion years old. Billion versus 200 million for ocean floor. Okay? So if you're looking for the young child, it's on the ocean floor. Okay? All right. So here's what those nasty rocks look like. They're a mess. We'll stop at this outcrop. That's in the Yankee Jim Canyon, one of my favorite spots. Great exposure to the basement there. And I really do love the basement. As much as I'm bad-mouthing it. Now, what we know from some really smart people doing some really good mapping and some really good geochemistry and piecing this all together is that the Wyoming block, I'll call it, or craton, or whatever term you like to use, they all use different terms, it doesn't matter. This block of continent that we live on, it started forming about 3.6 billion years ago in Montana. So the oldest continental material we have in Montana is 3.6 billion years. You guys with me on this? All right. But within those rocks are quartzites, which is just a quartz sandstone that's been smushed and altered, metamorphosed. And it contains crystals inside of it that yield dates of the origin that crystal formed, which was 4 billion years ago. That means it came from another rock that was formed 4 billion years ago and was redeposited 3.6 billion years ago in this sandstone that's been metamorphosed into quartzite. You guys with me? Okay, that's from the Beartooth. You can actually see it on the Beartooth Highway going up the road. It'll be covered in the Montana Rocks book. I'm not shamelessly promoting. That book out there, I get $1.50 for every one of those that are sold. I mean, I can't go to McDonald's on the money I'm making on these books. All right, so 3.6 billion years ago is essentially the first continental crust. The first continent of Montana is around 3.6 billion years ago. Where did that crystal come from that is older? We don't know. But we think that maybe the earliest crust of Montana was basalt, the stuff of the ocean floor. And it might have been at the top of a big plume of hot spot coming out of the mantle that was in what is today Montana. But we don't really know because there's nothing left of it. Crystals. So it's a guess, based on what little evidence we've got and what makes logical sense existed from. But at 3.6, we got rocks. We can go collect them and we can look at them and we can say, whoo, these were once part of the continent. Make sense? All right. And then the last big thing that happened is there was a major period of subduction at 2.8 billion years ago that intruded. Those of you who know the Beartooths know that you look at those rocks, and to your eye, if you're up at Beartooth Pass, for example, right, and you get out in that big parking area where the wind is howling, and you have the sorted circles. You've been up there. Some of you have been up there. And you look at those rocks and you're like, that looks like granite. And it does look like granite. It's granite nice. If you look carefully at it, it's got layering in it, which means it's been through that bloody metamorphic process. But it was once granite, like you might find in Yosemite. Okay? How did that form? It formed from an ocean floor subducting underneath the continent that was in Montana at the time, the Wyoming block. And it created a huge volcanic arc in Montana at that time that must have had big stratovolcanoes associated with it, like you'd see in the Cascades today. The magma chambers are these granite gneisses that we see on the plateau of the Beartooths. Everybody okay? A lot to digest, but we just started, so get ready. Burp a couple of times to make room, because there's more coming. All right, one last thing. Accreted on in this subduction, so what it tells us is plate tectonics was absolutely going on, okay? People ask, when did plate tectonics start? I would argue that plate tectonics probably was going on in some form right from the get-go. As soon as you had a hardened crust, you've got some kind of plate tectonic-like process going, right? With the movement of that hardened crust. Go look at a lava lake in Hawaii, right? The hardened crust moves around and blocks subduct underneath other blocks, and you can see it all happening. So it happened pretty early on, but if you wanted to ask a geologist who has very specific criteria for plate tectonics, probably say 3.6, and certainly by 2.8, there's good subduction going on and normal-looking kinds of volcanic rocks, or at least the magmas that are feeding them, that are being generated by that process of subduction of ocean floor. Okay? And then when there's subduction going on, you can have a variety of, you can have things that accrete on to the continent, blocks that accrete on to the from the subducting slab that won't go down, like India won't go down underneath Asia, so it accretes on. And it's not clear that that's the case for this, but this is the Stillwater complex, which is up near Nye, okay? And it's, of course, a very famous platinum and palladium deposit. And but to geologists, I don't really care about that platinum and palladium stuff, but what I do care about is this is a layered igneous rock. I mean, look at the layering in this igneous rock. We don't see that. Igneous rocks are blobs that crystallize blobs, right? Look at your countertop. Is it layered? No. Your granite countertop's not layered. But this is a layered igneous rock. And it's a Weirdsmobile. It's made up of really, really high, it's rocks we don't see at the surface very much today. The rock of the mantle, what's called peridotite. And then a partial melt that comes from it called gabbro. So it's a weird intrusion of interesting minerals like olivine and pyroxene and so on, which we just don't see very often. And it's layered, and really its origins are not well understood. I'm going to leave it at that because that's fair. It really is not well understood. People go from meteorite impacts to spreading, and this being ocean floor, to it being a thermal plume, like a hot spot, like Hawaii, you name it. There's a bunch of ideas. Some people think it's accreted onto the continent, others don't. Here's the point. We don't know everything. Isn't that great? I know enough to know that I don't know very much. That's great. That's how it should be. That's the beauty of science. All the rest of this I'm going over tonight is meaningless. What you should be left with is how much you don't know. You should walk out dazed and confused, to quote Led Zeppelin. I usually quote Bob Dylan, but that one just came out. All right. We had a collision called the Big Sky orogeny. This one we got down pretty well. Getting a little younger, so a little easier to see the evidence for it. There was a block, I'll just call it like India, it's called the Medicine Hat Block, and it collided with our continental crust, the Wyoming Craton. And the zone where it collided is called the Great Falls Tectonic Zone, running in a northeast-southwest trend. Right through, you can see here's Montana, so from the Dillon area up to Great Falls, and this is fantasy up here because it's in the subsurface and not something we can see. But nonetheless, we do know that we have exposures to the Medicine Hat Block. We have really understand the Wyoming Craton very well, and they collided. There was ocean floor that was subducting prior to it, probably generating that granite that existed at 2.8. Eventually in came a non-subductible, a piece of continental lithosphere, and it couldn't go down. It had the same density as our Wyoming continent, and it stuck to it. And it made more continent. Everybody good? It's called the Big Sky orogeny. What does the word orogeny mean? It means mountain building. Okay? I try to keep the word orgasmic away from orogeny, especially in front of students. But one thing you can see is, look at how beautiful this metamorphosed rock is. It's just gorgeous. So you have a layer, you have layering, but the layering is from metamorphism. It's from pressure and temperature that segregated minerals away from one another into those light and dark bands. And then the bands themselves were folded. And it may be, although they're still debating it, I talked to the folks that are the experts on this, it may be that this folding is evidence of the collision of that block and this block. All right, now we're getting to stuff I can get my head around. So starting around 1.47 billion years to maybe 1.5 max billion years ago, but what's 300 million years between friends? We started extending. North America had built itself into a large continent, and it was attached to other continents, and we had a supercontinent. Like that thing Pangea, that Wegener, which is younger. This one's called Nuna, and we don't really fully understand it because, again, the rocks are old. But I think it's showing up in consensus in the literature that Nuna existed, and it broke apart. And when it broke apart, one of the things that happened was the development of a rift in Montana that trends from southwest Montana kind of up to the northwest, up into Canada. And in that pull apart, which is a rift, right? So what's going on? Down at depth inside the Earth, convective cells are doing this. They're rising and they're moving apart from one another. That's taking the overlying lithosphere and it's pulling it apart. So the continent is being pulled apart. Everybody okay? As it breaks up, blocks drop down and blocks rise up. And eventually what will happen is one of these areas of downdropping block will take over as a major area of downdropping block and create a rift, right? Like the Red Sea or the Gulf, the Gulf of California, with Baja being rifted off of Mexico. So the Belt Sea was probably one of these places that was rifting apart, and it got invaded by ocean water that came in from up here to these are all present coordinates, right? They came up here from the northwest and came in this direction into the sea, making this sea. And it was clearly sometimes connected to the ocean and sometimes not. My advisor was goddamn Don Winston at the University of Montana in Missoula, by God. And the belt was what he did all of his life. And by God, the belt is a lake. There wasn't any ocean in the goddamn belt. And this is exactly how Don talked. Adding a few Christ commanders in there, shithouse rats, and a number of other, wonderful terms that I have no idea where they came from, but I've lived with them all my life and used them frequently. So Don was probably right that the belt also had times when it was a lake and was not connected to that ocean, and there were times when it was connected to that ocean. That doesn't surprise me because we see that on the planet today in rifts, right? Where they can be inundated by ocean water or they cannot. But what's neat about it is it was deposited at a time when the only thing on the planet that was a life form, for the most part, were cyanobacteria. These are bacteria that photosynthesize to make a living. And those cyanobacteria trapped sediment and created these weird domal mounds called stromatolites. And you can see them in Glacier National Park, right? Go to Logan Pass, and you walk the boardwalk out to Hidden Lakes. There's stromatolites all over the place in those rocks. If you really want to see them, cross the road after saying a prayer and get on to the Garden Wall Trail. And there's gorgeous, huge, cone-shaped stromatolites in the rocks there. All right. But what really floats my boat as a sedimentologist in these belt rocks is that they are loaded with ripple marks and mud cracks and raindrop imprints. Oh my God. Raindrop imprint from a storm that went across a mud flat 1.4 billion years ago, made a pockmark in the mud that got buried by more sediment, and then I walk by and see it 1.4 billion years later. That gets me orgasmic. That's pretty orgasmic right there. This is Flint Creek Hill down from Georgetown Lake. A must-see. Just watch the traffic. But that hill, what a great exposure. Mud cracks and ripple marks and so on. You have to deal with the crowds of Glacier National Park, right? But the park, I bow to the park. I've spent many years working in the park, and it's great. Glacier National Park. Not the park. I get into trouble down here saying that. Okay, so Earth was really more like Mars with a little bit of scum on it. Little bit of life, little cyanobacteria. Not much else. There's certainly no evidence of multicellular animals at this time. And so the reason why all this stuff is so well preserved is there was nothing around to churn it up. Sediments are loaded with organics. And if there is something to eat, it's gonna get eaten, right? So if those sediments have organics in them, they're gonna get chewed up and pooped out by an animal. And you're gonna end up with that being destroyed. So the sedimentary structures later on in the rock record disappear, if you will. I mean, they're there, but like in the belt, no. No, way less orgasmic. The minute animals got around to beating them up, it got less orgasmic. All right, how am I doing on time? Does it really matter? It's geological time. All right, so Around 900 million years ago, we had a meteorite impact hit Idaho, not Montana, and then the rocks got shoved into Montana. So they're ours. I don't care that it hit in Idaho. They're now in our possession. 9/10 of the law. So how do we know about this thing? This thing is one of the largest impact craters on Earth. It's like in the top 5, okay, known meteorite impact craters. Okay, there's no big hole in the ground. This thing is down south of Dillon on the scenic byway that we call the Big Sheep Creek Medicine Lodge Scenic Byway, or whatever you want to call it. It's got a zillion names, but it's the Big Sheep Creek over the Medicine Lodge down in the Dillon, south of Dillon. It's awesome. How many of you have been on that? Yeah, it's awesome. You got to do it. It's absolutely worth doing. All right, now I just sent all of these people down there. What kind of a dummy am I? And there's great fishing down there. Okay, forget I said that. It's awful. So at the pass between these two drainages, the Medicine Rock and the Medicine Lodge and the Big Sheep Creek, is where this impact is. And there's not a hole in the ground. What there are these very phallic-looking, conical-shaped rocks sticking up all over the place out of the ground. And notice they're striated or grooved. Do you guys see that? All right. And they're cones. Now, this one, is my favorite because it's particularly phallic-looking. Most of them are kind of more cone-shaped, like your dunce cap. But what happened is when the meteorite struck the ground, it sends a shock wave into the subsurface, and it pushes rock past rock like this in a downward trend. And it creates the cone-shaped, slicked rocks, or grooved rocks. Make sense? This thing's a quartzite. And that quartzite should have been a layered rock of quartz sandstone-like rock, but it has these grooves and these cones, and once you see them, you look around on the ground, and you're like, oh my God, there's cones, and thousands of them everywhere. And they've been mapped out, and that's how we know the size of this impact, is by mapping out the distribution of these cones. So that's a minimum size for this thing. It was a whopper, okay? What it did, on the planet, I don't know. There weren't much in the way of multicellular life around at 900 million years. I mean, we give eukaryotic cells by that time. So this wasn't good for sex, or cloning, because we had prokaryotes, right? Cyanobacteria. But again, the record's old and it's hard to know what really happened. All right, so then at about 520 million years ago, all of these mountains that had been created earlier by the collision of plates and the making of the Wyoming Craton and the Big Sky orogeny and the uplift of big mountains by these collisions that happened during the basement time, there was a long period post-belt where they were eroded. So Bob Dylan asked a very important question once. How many years can a mountain exist before it is washed to the sea? I have the answer to that question. That rock right there is 1.8 billion years old. It's got a dike through it, see it? That's an injection of liquid rock, of magma, through a layered rock that was metamorphosed by heat and pressure, not by layering of sediment, by tectonics. And then it was cut by this dike, and then it's eroded off. And sitting on top of it are pieces of the dike, right here, and they're mixed in with a sandstone that's above it, called the Flathead Sandstone. And this sandstone's 520 million years old, and it rose up, global sea level rose up because there'd been a supercontinent right before it. And there had been ice all over the planet a period of time we call snowball Earth. And these two things combined, getting rid of all that ice and the breakup of this supercontinent, which is called Rodinia, caused sea levels to rise around the globe. And it rose up over the eroded surface of North America. And so we have that contact. We can go look at it. You can go put your finger on it up here in the Beartooth. Okay? Sunlight Basin in Wyoming. As much as I hate to give credit to Wyoming for anything, you drive out the Sunlight Basin, there's a beautiful bridge that crosses across this deep canyon. I've forgotten the name of the canyon. Somebody can help me. What is it? It's not the Clark Fork. It's a tributary coming into the Clark Fork of the Yellowstone. Sunlight Creek, thanks. That's the, well, duh. Sunlight Basin. Gorgeous spot, right? And there's the boundary is there. This boundary between this beach sand and the underlying guts of a Himalayan-sized mountain chain that was eroded down to sea level. And then sea level rose up and laid these beach sands over the top of it 520 million years ago. And you go put your finger on it. Okay? And we can map it out. And we've done that. And it's flat. I mean, like pancake flat. And there's a few islands here and there, and they're nothing to write home about. Right? Gilligan would not have survived on one of these islands for a 3-hour tour. They're not much. Molehills. Okay? And they got buried by the rising sea and its beach. So it took from 1.7 billion to 520 million to wash the mountain to the sea and make it flat so that the sea could then rise up and transgress over that surface and bury what was the old mountain range, which was now completely eroded away and flat. The continent was flat, like Australia flat. Worse. Flat, flat. Okay, most of it, at least here in the West. Okay, so how much time is that? Well, 1.7 billion, 520 million, easy math, say 1.2 billion years. Right? So somebody give a call to Bob and let him know. It takes 1.2 billion years that a mountain can exist before it is washed to the sea. And of course, that's variable depending on the rock type and all these other things. And he needs to know that. All right, so there it is. So this diagram shows how this happens. Sea level rises up and it lays down the beach sand, and then offshore muds right here are laid down over the top of the beach sands, and then offshore lime is deposited over that muck. It's called a transgressive sequence because the ocean has transgressed across the continent and made this pile. And so in Montana, we go from that sand to a mud called the Woolsey Shale to a lime called the Marr Limestone. And it represents this sea level rise of the beach going inland, followed by the muck, followed by the lime, making a stack. Okay, it went all the way in to almost Minnesota, where there was a bit of a topographic high we call the transcontinental arch that separated the incursion from the east from the incursion from the west. So the source of that sand, eventually was this, land here. And the lime was made by animals. By this time, the oceans are teeming with multicellular life, and those things learned how to create a house that protected it from predators, a shell. And the shell probably evolved, frankly, as a way to get rid of calcium carbonate that was in the water that they precipitated out of their cells as a waste product, and then all of a sudden it's like, oh, this is good. That's how evolution works, right? It's not thought through, right? They don't like, I need a shell. That's not how it works. Something happens, turns out to be good, boom, it gets passed on. That's it. Nothing special. All right. Then it just gets better. The seas go in, and the seas go out, and the seas go in, and the seas go out. And this goes back and forth, and Margaret, you can hear Jimmy Buffett, wasting away again in Margaritaville, right? And you can look at the rocks for yourself. Okay? Get on the boat at the gates of the mountains in Helena and go into the canyon and get off at the rest area when they ask you to go pee, and they give you literally no time at all to pee. I mean, please. Have you been on that tour? My God. I mean, you couldn't pee in the bushes with the time they give you, let alone 50 people on a boat waiting for a pit toilet. So I don't pee, I go look at the rocks, and in the rocks are corals and crinoids and brachiopods and all these animals that are still mostly around with us today in some form. And how do they make a living? They make a living in warm, tropical, marine waters where they filter it for particles of organics to make a living. So it has to be clear, warm water that's not got a bunch of sediment dumping in on it, so that they can filter the organics that are in that water. Because otherwise they clog up. Filter feeders clog up. They can't be in water full of sediment. So you can imagine that Montana at 350 million years ago, which is right here, at the time that these guys were alive, crinoids, brachiopods, rugose corals, there's a brachiopod, okay? Some of the creatures, and these guys are all over in the rocks in the gates. Why? Because those limestones that make up the gates were deposited in a shallow tropical sea right here 350 million years ago. Because the seas went in and the seas went out. And it stacked up. Why did it stack up? I'm curious why you think. How do we get that stack? How do we stack it up? If I am the sea level rising and falling, and I should wipe out what I have deposited, right? Not make a stack. What has to happen to this stage for me to grow a pile of rock moving back and forth? It has to fall. The weight of the sediment causes the continent to sink into that mush layer below and add more sediment. Got it? That's how you get that big stack in the Grand Canyon on the basement. The ground subsided under the weight of the sediment it has accumulated, allowing for more sediment to accumulate. That's how we get the stack. Make sense? All right. And then this diorama, I don't know if any of you guys know Doug Henderson, but this guy is a genius artist. He lives in Whitehall. I mean, no offense, but Doug lives in Whitehall, and he's a genius. You should see his dinosaur paintings. My God, this guy's, all right, I'm going to go out on a limb. This guy's the best artist in the state. No offense to any other artist. And who's ever heard of Doug? Anybody in here? All right, good. He's not well known, right? Because he does creepy stuff like geology. but he's a genius. God, his stuff is good. So I used this. This is on a Lewis and Clark geology road sign down at Clark Canyon Reservoir that I put in during the bicentennial in 2005. And he did this for us on the Madison limestone. So the stuff that you see in the gates of the mountains, that's what it looked like over Montana at that time. It's really, his accuracy is really good. God, that thing's good. Okay. I'm so glad I was able to talk him up at this. This is, it's deserving. He's a common Yellowstone visitor too. All right, so we had formed that supercontinent of Wegeners called Pangaea by this time, right? And it is breaking up starting around 250 million years ago, or a little bit before then. It's starting to break up. And here's that breakup right here. So the North Atlantic and the South Atlantic Ocean. So the collision involved, of course, creating the Appalachian Mountains that formed Pangaea, as Africa and Europe collided with the eastern seaboard of the North American continental mass. But make no mistake, South America was also involved, and it collided with the southern part of North America. And there's remnants still of that, and places that we consider flat, and like Oklahoma. But there's remnants of that there. Okay, so the breakup of Pangaea changed everything, because what it did is it took the North American continent and it started moving it this way, and it's in contact now with the Proto-Pacific Ocean out here. And what's going to happen to that ocean? Yes. All right. God, I reached one person. What's it going to do?
Subduct.
Oh. There's a picture of it. Okay? So the Farallon Plate, it's called, ocean floor, started colliding with the North American continent. As it descended, it generated magmas that rose up and created chains of volcanoes on land, like you see with the Cascades. And it also crunched all of these sedimentary rocks that had been accumulating on the basement, and it created what we call the fold and thrust belt, which just means everything above the basement got folded and shoved to the east along faults. Fold and thrust belt. Everybody okay? All right. And it's all due to the breakup of Pangaea. So Pangaea breaking up drives the continent into the Farallon Plate, and the collision of the two causes volcanism and magma intrusion and the fold and thrust belt. And the other thing it did is it down-warped the land to the east of the fold and thrust belt, and it created what we call the Western Interior Seaway, which ran from the Arctic Ocean to the Gulf of Mexico. Was there a problem? Okay, so this big, long north-south interior seaway, dinosaurs lived along the edge of it. Inside of it were swimming plesiosaurs and ichthyosaurs, these swimming reptiles, right? The Loch Ness Monster. And the big coiled squids, ammonites. Ever seen an ammonite before? Okay, these are these big coiled squids. Okay, you can collect them along the shores of Fort Peck Reservoir. They come out of the Bear Paw Shale, and you see them along you can just walk along during low, when is it not low? In Fort Peck Reservoir. Whenever it's low in Fort Peck Reservoir, which is today, tomorrow, and the day before it, and collect these things that just weather out of the rock. I have one in my office this big around. Mother of pearl still on it. Awesome. Okay. There's one in the Denver Natural History Museum, 35 feet in diameter. These guys were big. Not all. Some are little tiny ones like this. Right? Like anything. but they were voracious predators, and they lived in this ocean. And we know that it was ocean because we find them in central and eastern Montana, right? Which is not ocean anymore. So it was then, and that's why. Because of this collision. The collision down-warped it and made this ocean. And that ocean also waxed and waned. You know, there were times when it came in and connected fully, and there were times when it didn't. And that went back and forth throughout what we call the Mesozoic time period. Really starting in what we call the Jurassic, and that's a time period we all know because of Jurassic Park, right? And the dinosaurs of Jurassic Park were living on the margin of that seaway. Okay? Guys with me? All right. So north of Dillon, we've got these guys. They're in a formation called the Kootenai Formation, which is of this time period of this interior sea, and they were living along the edges of it. And for years, people thought there's a famous formation in Montana from Jurassic time called the Morrison Formation, and it holds the Dinosaur National Monument dinosaurs in Vernal, Utah, right? Which was found, by the way, a little bit of trivia for the historian. The very first master's thesis in the state of Montana was Earl Douglas at the University of Montana, 1899, school teacher from Ennis, Montana, who went back and got his master's degree at UM, the very first master's degree, and he went on to find the dinosaurs of Dinosaur National Monument in Vernal, Utah. Montanan, by God. And the first graduate of the University of Montana's graduate program, which is super cool. And a public school teacher from Ennis. That's how he got started. Okay, so forever people thought, there's no fossils in the Morrison, in the Dillon area, you know, and I used to tell students that they're out supposed to be making their maps at field camp, don't be spending your time. There's always one, right, that is like a maniacal about dinosaur fossils, right? And so they're not gonna make their map, and I spotted this one kid, and I went up to him, I was like, look, I don't want to see you walking parallel to the Morrison Formation. Walk perpendicular and draw lines on your map. That's your job at field camp. And so sure enough, I found him one day, and he's walking parallel to the Morrison Formation like this. Okay, which is not how you map. That's how you look for bones. And I said, find any? He pops up, I did. And I'm like, what? He brings me back. There's a bloody dinosaur in the rock. Like the whole thing is there in the rock. And I'm trying to remain calm. Yeah, you know, they're all over the place out here. So let's just go home. Not deal with this. I get on the phone. Jack Horner, who I've known forever. Jack, I got a dinosaur in the Morrison Formation. He's like, I work on the Cretaceous. Nobody interested. So I went out there. And Jack said, okay, you need to get that stuff out of the ground because it's going to walk away. So get it out of the ground. I got the permits, went out there. One of the things I collected was this. Okay, that's a centimeter. Okay, that's a toe bone from Littlefoot. So for those of you who learned your paleontology from Land Before Time, this is a Littlefoot from Littlefoot. A sauropod dinosaur that along with, it turns out, 15 others tried to cross the swollen Morrison Stream and drowned. So here's a Jurassic tragedy involving children. And we still don't have it out of the rocks. One of these days. But its dinosaur work is hard. It takes money, time, big equipment. It's not easy. I worked with Jack for a summer getting dinosaur eggs out of the Milk River country, getting dinosaur eggs out of the Two Medicine Formation. This is where the original dinosaur nesting sites were found out of Shoto, right? And to the north, in that same unit, are more of them. And we had this clutch of eggs, 25, 26 eggs. It's awesome. The work, oh my God, to get this thing out of the ground, the work was unbelievable. I mean, we spent weeks and weeks and weeks and weeks, digging around this thing to create a pedestal that we could then plaster jacket, right, to hold it together. And then you got to get it off the mountain, and it weighs a ton, literally. So using techniques that probably were used by the Egyptians, we rolled it down the hill on a piece of plywood, and eventually it had to be picked up by a cherry picker on a truck and put onto the back of a gigantic, like semi-style truck, not like a pickup truck. If you'd have put it in a pickup truck, it'd be like this. Dodge Ram, forget it. It's not going to do it. Okay? All right. So as we go into the late Mesozoic, this sea level, the interior, the western interior sea really gets rolling. So you can see that the eastern half of Montana is under that ocean from time to time. Again, it waxed and waned during the what we call the Mesozoic. Many of the great dinosaur finds in Montana come out of those units. Jack did this reconstruction. You can see that. It's at the Museum of the Rockies in Bozeman, but I'm going to give a pitch to the Two Medicine Museum in Bynum. Got to go there. Okay, north of Shoto, Bynum, don't blink. There's a great museum there. It's wonderful. It's absolutely worth a stop. And they've got this reconstruction. Jack did this reconstruction of this baby Maiasaur. So Maiasaur was the famous mother dinosaur, right? The hadrosaur, the duckbill dinosaur that Jack wrote books about and so on. And that's where the egg clutches are at Egg Mountain. And he took a bunch of bones from different animals and reconstructed one juvenile dinosaur out of it. So it all comes to an end at the end of the Cretaceous with the extermination of these, what probably is on the order of about, at least 75% of life on Earth. And the consensus is widely now that a big rock from space, right, hit the Yucatan Peninsula, that would be down at the Gulf of Mexico, and it created a nuclear winter scenario. Mass extinctions are my area of specialty as a grad student, and one of the things that people always ask me, well, what causes mass extinction? And they're always interested in the dinosaur mass extinction. Think about it this way. I'll leave you with this. All right, first of all, mass extinctions are always many bad things happening all at the same time, right? No place to run, no place to hide, overlapping change that's bad, 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 and you get mass extinction, okay? Whether it's a rock from space or whatever, there's all kinds of change going on at the same time. That is really how you get an extinction. Okay, then, what's the kind of the big change that we see on the Earth that causes extinction? Well, think about it. How is life distributed on the planet? Where is the vast majority of species on this planet? Think about the planet as a whole, and think about it with regard to the poles and the equator. At the equator, on land and in the oceans, the vast majority of the diversity, is what I mean, the diversity of life on Earth is 15 degrees north and south of the equator. And it diminishes from there to where you have the least species diversity where it's cold. Okay? How many people are in Montana? 1 million. All right? There's a reason for that. How many are in Florida? Okay? Cold is crucial to extinction. All right, how does a meteorite strike create cold? Blocks out the sun. Blocks out the sun. It created a nuclear winter scenario, right? Where the sun got blocked out, photosynthesis collapsed, the whole food chain, everything went to hell in a handbasket. But cold is a part of the KT boundary extinction at a time when it's super warm, right? There's no ice at the poles, as John was talking about earlier. Yet it got cold. We know this from the geochemistry, that it did. Okay, but there was all kinds of bad things going on. And they were happening before the rock hit as well. All right, enough on mass extinction. Oh, I should have pointed out. That is the mass extinction right there in that coal. It's called the Z coal. This is out in Makoshika State Park. Great place, gotta go. Okay, and somebody, the guy who's the current super of that park, he knows where the boundary is and can show you where it is. It's interesting, the boundary is actually in the coal layer. It's not at the base of the coal, it's not at the top of the coal, it's within the coal itself. How do we know? Because when you chop open that coal, there's a clay layer inside of that coal, it's the fallout. How do we know it's the fallout? It's full of fallout debris. It's got little glass blobs in it that are called tektites that are from melted rock that fell out of the sky. It's got, quartz crystals that were damaged by the impact. It's cool. And it's in the coal. And people are like, how can it possibly be in the coal? Coal is a peat bog. It landed in the peat bog and accumulated. That's exactly where I would expect it to be. Okay? If it landed on a stream, the stream's going to wipe it away as it keeps migrating back and forth. But if it lands on a peat bog, it's going to get preserved. So the KT boundary, the dinosaur extinction boundary, very commonly occurs in the coal layers. That's why. Okay, I'm going to speed it up. How am I doing, John?
You're doing great.
Okay, good. I can look at the time. Oh, God. Okay. Here we go. We're going to roll now. Okay, so this collision that occurs between the Farallon Plate and North America, remember I said it folded and it faulted the rocks. Here's the evidence of that. Chief Mountain. You guys been up Chief Mountain, north of the northern end of Glacier National Park? That's part of what's called the Lewis Thrust, which is a big fault that ramped up and it shoved old belt rocks on top of those western interior seaway shales filled with ammonites that I was just talking about. Older over younger. Remember, the pile accumulates on the windowsill, getting younger, right, up from the bottom of the windowsill. If there's disruption to the pile, something's happened. And collision of plates will disrupt it. And it'll shove rocks up and over other rocks, and you'll get older over younger. Everybody good? All right, it's called thrusting. And here's another one. This is in Sun River Canyon. Ever been there? Oh my God, Front Range out of Augusta, you gotta go. It's awesome. I mean, even if you don't care about the geology, it's a great place to go. But I know that's not the case. Right? Okay. So here's that Madison limestone with its crinoids and its brachiopods and its corals, and it's shoved over the Cretaceous shales with its ammonites and stuff that was living in that interior seaway. So older over younger. There's the thrust fault right there. There you can barely see it. There's my student right there. Pointing. She's now an interpretive ranger in Glacier National Park, I'm proud to say. Okay, kid from Minnesota. All right, so here's an aerial view north of Dillon along the Big Hole River. And what you see in this Google Earth image are gigantic folds, one after another, after another, after another. See them? all right? It's kind of hard to envision them from the air, because in the side view, you can see that's a downfold, right? That's like a layer of, paper, bunch of papers stacked up that you squished and it folded down. From the air, it's kind of hard to see that. Whoops. You instead see these pointed shaped things, and it's just, you're taking this folded layer and you're chopping the top of it off. So you see the layers dipping this way, the layers dipping this way. Got it? Where it points together is because it's tilted down into the ground like this. So they come together, those layers come together across that point where they hit the ground. Okay? This is why everybody and his grandmother's brother comes to Dillon to map every summer. It's called Block Mountain, and these folds and faults are what they all come to map. It's the best place in North America to learn geology, bar none. Public land, this is all BLM land, and I got worried years ago that it was going to be given away in a land swap, and so I got it set aside as a research natural area. So it's primary, it did nothing. The guy that ranches out there is a buddy of mine, and it does absolutely nothing to anything that was happening out there before. But if somebody wanted to develop it for oil, gas, or minerals, that would be a harder thing to do because the priority is this educational value. So I'm proud of that. This has been a $1 billion industry for Dillon over time. I mean, I know that each summer they're making millions of dollars on students. Think about it. Bars, grocery stores, tire shops. Do you know how many tires these guys go through? What's that?
The taco bus?
Yes, the taco bus. I mean, the taco bus is making a mint off of those geos. And the town loves the geos. They really do. They embrace the geos, and it's been good for Dillon. And that was the value of this land as public land, was educational. And so that got signed by George Bush. So there you go. Flaming pinko like me and George Bush. Got it done. All right. So this fold and thrusting that's going on is also getting injected by these magmas that are forming because that ocean floor is descending. And as it descends, it heats up. And as it heats up, it releases water. And when the water is released, it hits the overlying rock in the mantle, which is in a hot, mushy state. And it's like putting salt on ice. What happens when you put salt on ice? It melts. That's exactly what the water does. It causes melting. And then those blobs of liquid are under pressure. So like a lava lamp, what do? They rise. And some make it to the surface. And they erupt as volcanoes. And so here's a map that shows the outline of them. Intrusive in red, extrusive in orange. That just means the magma down low, the volcanoes up top. And you can see the distribution of them from this time period, the Cretaceous, in western Montana. Okay? So you've got a whopper right here. Anybody know what that is? It's called the Slide Rock Volcano. It's out of Big Timber. Almost nobody knows about it. It's cool. It's a single volcano, all by itself. I don't know why. There it is. The other one is the Adels. Oh my God, that beautiful canyon on I-15 on the way to Great Falls, right? Fishing heaven on the Missouri. You go through those dark volcanic rocks on I-15, going to Cascade, and I don't want to diss Cascade, and then on into Great Falls. That's another big volcano from this time period. And then the biggest of the big is the Boulder Batholith, right? Which goes through the most important city in the state of Montana. That'd be the holy city of Butte, Montana. And you can tell everyone you know that Rob Thomas said that Butte was the most important place in the state of Montana. Because I'm afraid of people from Butte. And you should be too. All right, so this subduction zone starts to flatten out, and there's a lot of controversy over this right now. But since I was a geological child, we have been talking about flat slab subduction of the Farallon Plate, that it was subducting at a normal steep angle when it started, but the point of spreading that was creating the ocean floor, it was moving its way towards North America. That means that the ocean floor that was coming out was hotter and more buoyant, right? Well, something that subducts that's hotter and more buoyant is going to subduct at a shallower angle than something that's old and cold and dense and is going to, fall into the mantle. It's always made sense to me. John, what do you think?
I thought you did that.
Okay, good. That was the right thing. There's a lot of people challenging it these days. They do imagery deep into the earth called seismic tomography, which is a fancy word to say that they're sending seismic waves down into the interior and looking at the reflections. And there's a talk that we geologists have about geophysicists. When you talk to a geophysicist, the answer you get from them is, what do you want it to be? Right, John? What do you want it to be? So they've got these computer models from the seismic data, and one person sees the Yellowstone hotspot emanating from about 200 kilometers down, and another sees it down 600 kilometers. What's the difference? Different computer models? The data are all still the same. One person was drunk while they were looking at it on the computer. I don't know. It's remote sensing. I like what I can touch. And I like what seems logical to me. And the ocean floor getting hotter as the spreading ridge, the place where it forms, is getting close to the edge of North America, making the ocean floor that's coming in hot and buoyant. And it makes me think that should come in at a shallow angle as it goes under the continent. It's going to be harder for it to sink easily, right? It's lighter. It's dense. It's not as dense. It's hot. So it's going to scrape underneath the continent. Well, if it scrapes underneath the continent's going to feel that, and blocks are going to pop up. It's called the Laramide orogeny, and it's what popped up the Beartooths. First time. The first time. Actually, not even the first time, because they were high during the Archean, the basement, right? Back in the Bob Dylan years. But the most recent time that they popped up was during this. So shallow subduction created these block uplifts. The Pryors are an example, the Beartooths an example. Down in Wyoming, all those ranges are examples, right? The Bighorns and the Winds and so on. These are all basement chord uplifts from this, what I like the shallow subduction model for doing it. Okay, so here's the Beartooth block popping up. There's Beartooth Butte. And what it did is it took all the overlying sedimentary rock that was sitting on top of the basement, and it curled it over this block of basement that was rising. So along the front of the Beartooths, the rocks are tilted up on edge, forming palisades. But at Beartooth Butte, they're flat, sitting on top that Beartooth block. That's connected. Shoo, like that. Got it? And this fault uplifted that block and caused it to curl over that rising block, and it's been eroded away in between. Does that make sense? Everybody okay with that? All right. Good, because I'm not changing the story. I had to throw in a local one because we're going to see it tomorrow. Recognize that? Yeah. That's one of these sections of sedimentary rock rolling over the basement from the Gardner Fault. So the Gardner Fault is an old Laramide fault It brought the basement up, and the sedimentary rock above it curled over the top of it, and you can still see the curl. So the least interesting thing about Devil's Slide is that stupid red slide. That is like not interesting at all. That's the Chugwater Formation. It's a Triassic red bed. It's got no fossils in it. I mean, it's just dull as red dirt. All right. The other thing that happened at this time is there was a lot of coal that formed. Montana, in the eastern part of Montana, the sea was retreating. It was into North Dakota, thank God. And as it did, it left swamps behind, and those swamps accumulated plant material and got buried by streams, and you get the coal seams. Okay? So coal strip is from this time period. It's called the it's Paleocene mostly. Well, the old days we used to call it tertiary. Okay, so it's post the dinosaurs. The coal is post dinosaurs, most of it, not all of it, but the stuff we're mining is. Okay, and that's a reconstruction of why you have it all in eastern Montana. So it was actually these uplifts, like the Beartooth uplift, which were shedding the sediment that came out as streams that buried the swamps that made the coal. So the Beartooths are critically important to the coal because they're the source of sediment that came out as streams over the top of the peat bogs and buried those peat bogs and made coal. Make sense? All right. And then my favorite part, the coals got set on fire. And they would burn underground and create clinker. Clinker is metamorphosed rock above and below the seam of coal that burned out. And it's awesome. It burned the coal out, and then it would collapse, and you get breccias and weird structures. Sometimes it would bleed out onto the surface. Look at this. There's a drip. That's a drip of burnt rock from a coal seam that burnt the sandstone, turned it to a liquid, and then it dripped out onto the surface, making that drip deposit, which solidified as it was dripping. That was an orgasmic find right there. That's all I have to say. Okay, so then we have these big volcanoes in the area that are from this continued subduction going on, in my view. Maybe the beginnings of extension, called the Absaroka volcanics. Up in central Montana, they're called the Central Montana Alkalic rocks. We'll look at both. All right, so the Absaroka volcanics down here, those are what we'll see on the trip tomorrow. And these were big stratovolcanoes. We're talking like, Mount Rainier-like volcanoes. And when they would erupt, they would produce lahars. And the lahars are just volcanic flows of cement-like material going down a river. So it's a viscous flow of volcanic debris during these eruptions. The water is coming usually from like ice that was on the cone. This is on Specimen Ridge. These are the metasequoia, the redwoods up on Specimen Ridge in the park. Okay, best place outside of the park to see some of these, in my view, is the Gallatin Petrified Forest down the Tom Miner Basin. That's getting pilfered. But you got to get up high, right? The King of the Ram's Horn, and there's several others. If you get up high, if you're willing to, hump it up, you can get to some good ones. And then the other is on Specimen Creek, south of Big Sky. But watch for bears, because there was a person mauled, I think killed, right? A year or two ago. Solo hiker, not good. All right, this is Highlight Canyon. And what you see, this is Rainbow or Palisade Falls. And so easy place to get to, it'll be covered in the book. And what you're seeing is down here is a lahar from these old volcanoes, and it was in a stream valley, and then it erupted a lava flow, and the lava flow went down that stream valley and covered it over. Where are the volcanoes? They're long since eroded away. What's left? The deposits that went down the river valleys in the low areas. That's what's left. Okay? How do we know where the volcanoes were? We can actually see the stalks or the plumbing systems for where the volcanoes were. Bunsen Peak in the park, that was a volcano. There's one on Washburn. Guys with me? Okay? So we can actually figure out where the volcanoes were. We know where they were. We know where a lot of them were. I'm not going to say we know where they all were. Okay. Keep moving. Central Montana, Alkali Province. If you haven't spent time out in central Montana, it's way better than it sounds. Okay, here's Lewistown, somewhere down here's Lewistown. These are the Judith Mountains. Okay, these are the moccasins. Okay, these are laccoliths. They're intrusions where a dike fed into layers that went horizontal. They went as horizontal as far as they could, and then they reached a point of neutral buoyancy where the overlying rock, and they started blowing up like this. So what you get is a very weird structure that has a flat bottom, a domed top, and a feeder dike. Okay, then erode the overlying sediment away, and you get a dome. You get a dome. You get a dome. You get a dome. Look at Google Earth in central Montana. There are domes everywhere. They're all laccoliths, just about. An exception, south of town. Big timber in the crazies is a stalk. What's a stalk? That's the plumbing system from one of these old volcanoes. So in the crazies, the main magma chamber in the crazies is not a laccolith. But you go north in the crazies, and I don't have that on a map here, but if you go north of the crazies, you got laccoliths as you head up towards the Castle Mountains. They're all over. Okay, so they're mostly laccoliths with a few stalks, like this. Okay? All right, what's weird about them? They're full of sodium and potassium with very little quartz, what's called an alkalic igneous rock. It means nothing to the layperson. It barely means anything to me, but they're rare. And we have a specialty of our own here in Montana called shonkinite, which is named after the town of Shonkin, which doesn't really exist any longer, but is up the Highwood Way, north of Great Falls. And it is a rock that looks like basalt, but it's loaded with sodium and potassium, and that doesn't occur in basalt. Ocean floor does not have a lot of sodium and potassium in it. So what in the heck is this basalt-looking rock doing out in central Montana full of sodium and potassium? Well, the reason is that there was shallow subduction going on. And when you subduct shallowly, you put more pressure down on this underlying mush layer, the asthenosphere, and it melts under high pressure. And lab experiments show that the way you get shonkinite is a weird rock of central Montana is through high pressure melting, which further makes me think that that flat slab subduction was going on, because it creates more pressure on the underlying rock. It melts it at a higher pressure. Right? Look at this. If you've never done it, float the White Cliffs of the Missouri. That'll be in the book, but that doesn't cut it. You've got to float it. Okay? This is a dike of shonkinite cutting through the Eagle Sandstone, which was a beach deposit in that Cretaceous interior seaway. Isn't that cool? I mean, it's hot, but it's cool now. Sorry, I lost myself. All right, then everything starts falling apart about 50 million years ago. All this compression turns to extension. Everything starts falling apart. I think the way to think of it is the plates colliding is like a bulldozer pushing against the continent, And it backs away. And the reason why it backs away is because we're adding pieces of continent to North America, building Oregon and Washington. Okay? Because the edge of the continent used to be in Idaho, in eastern Washington. And we've added all that land on. And as we added that land on, that moved the point of collision and compression away, and it's like a bulldozer backing off the pile, and it fell apart. Y'all with me? Okay, I think that's the simplest way to think about it. And what it did is it created low angle faults that unroofed mountains that rose up underneath. So the Bitterroots are the best example. Let's start here. So the Bitterroots, look at this surface. See it? All right, that's called the Bitterroot Dome. And it is a block of the Earth's crust that was rising up. And as it rose up, sliding off of it was the sapphire block, the block that makes the Sapphire Mountains, and separated by the Bitterroot Valley from the Bitterroot Range. Think of it like this. Y'all with me? The dome rises, the rocks slide off and make valleys. You got it? The Deer Lodge Valley formed this way. It came off of what's called the Anaconda Metamorphic Core Complex. This was rising, and the Boulder Batholith slid off of it, and it created the Deer Lodge Valley. That's when it started. Okay, the Big Hole Valley likely formed this way, and the Cashenan Valley, and probably the Mission and Flathead Valleys started forming this way 50 million years ago, but we don't really know yet. People at the Bureau of Mines in Butte are working on it. All right. Inside the rock, you can see the shearing of this unroofing process. See the layering in it? I mean, the arrows, make you have to see it. But I can see it. Can you see it? All right. That is the front of the Bitterroot Range outside of Stevensville. And what it is it's the inside of this unroofing as it's coming like a deck of cards sliding off. Guys got it? These rocks are messed up. They are smeared out. When this happened, it was hot. These rocks were hot and mushy as they were extending and pulling apart. And it just smeared them. It's a rock called myelinite, which is just a smeared mess of a rock. Then those faults, as they're doing this, they start to steepen up. Guys with me? They start to steepen up. And that steepening up is the beginning of the formation of the basin and range. So here you can see the crust stretching, rising, and like the top of a loaf of bread, breaking with very high probability of rupturing a 7.5 magnitude earthquake. The good news is, probably nobody down there lives in a Victorian like I do in Dillon. But you're in those homes that are stick-built. But it will not be good for Livingston, nor Dillon, which has the same thing going on. All right. The valleys, as they drop down, form basins. The basins are commonly interiorly drained. That forms lakes. In the lake sediments, look at that. I collected that guy. A fossil insect. Awesome. Tons of plant fossils, fish fossils, all the things that occur in lakes. So a lot of these interior valleys that had formed as we got basin and range started had lakes. They just didn't drain out. All right. Getting there. Hang with me. the hotspot shows up. 17 million years ago, the Yellowstone hotspot emerges at the three corners down here between Idaho, Oregon, and Nevada. And when it did, it domed up the crust of the earth around it, and flow went off of it radially, off that bulge. And I have been studying now for 30 years the flow of the ancestral Missouri River off that thermal bulge. Why do I care? Because A, it tells me the age of the mountain ranges that are now in its way, because rivers don't flow up and over mountain ranges. And it is loaded with the deposits of mega volcanic eruptions from past calderas of the Yellowstone hotspot tract. Look at this thing. We call this You Bet Your Ash. This is my oldest daughter. She works for YF. And this thing is unbelievable. This is from a mega eruption of the caldera about 10 million years ago when it was near Twin Falls. And it got into the Missouri River and it flowed into Montana. And the Missouri River at the time flowed into Canada and went into Hudson Bay. And we've been able to find this ash, which is, you can fingerprint it geochemically. So you can say, absolutely, that is that ash. We can be absolutely certain, because every volcanic ash is unique. It has a fingerprint signature. And the geochemistry we know, we found it in deltaic deposits that were deposited in Hudson Bay. Isn't that neat? Okay, that was a bad day. Okay, you know what else it did? It went over Nebraska and it killed a bunch of rhinos. Anybody been to that fossil site in Nebraska? Unbelievable place. What's it called? It's called Fossil... Ashfall, thank you. Awesome place. And it's the same ash. It's You Bet Your Ash. Okay? This one went as a lahar down the ancestral Missouri River. The one in Nebraska fell from the air. But you can be certain that was just a bad day on Earth. Okay. So that ash allows us to reconstruct the age of the mountains. And when, the mountains get younger as I get older. So when I was a graduate student at Missoula, I was told, wow, the mountains and the valleys we see in southwest Montana have looked like that since the Eocene for the last 50 million years. They haven't really changed. The valleys are the same and the mountains are the same. And then it was like, we found the Timber Hill basalt flow, which we could trace geochemically back to the Heisey volcano on the Snake River Plain near Rexburg. All right, well, it doesn't take a genius to know that between here and this is near Dillon. This is just east of Dillon. This basalt flow is up here. Here it is down here. Now, either that was one incredible fall of lava, which it was not, or it has been cut by this active fault, the Sweetwater Fault, which it has, and offset by about 700 feet. So what it means is the Sweetwater Range is younger than the age of the basalt. So we get an age in the basalt, it's 6 million years old. We know that that mountain range is less than 6 million years old. I was told it was 50. It's now 6. Actually, it's 4.5 when you add a little extra on top of that basalt flow. Okay? So what that means is that from 16 million, give or take, to 4.5 million years, give or take, the ancestral Missouri River was flowing like this. And if you don't know where you are, here's the Beaverhead Mountains on the Continental Divide. Here's the Red Rock, here's the Tendoy Mountains. Here's the Red Rock Valley. Here's the Mission Hills. Here's the Blacktail Deer Range. Here's the Sweetwater Range. Here's the Ruby Range. Here's the Tobacco Root Range. Dillon is right here. See that range? Wasn't there 4.5 million years ago. Neither was that one, that one, that one, that one, that one, that one, or even the tobacco roots weren't there. How do we know? Streams don't go up and over mountain ranges. They weren't there. How old are they? They're the age of the youngest thing, cut by the fault, which is actually something younger than this basalt. Well, that's how we know it's about 4.5. All right. What caused it? The hot spot moved to its present position. And what the hot spot does is it bulges everything up. So the bear tooths are bulged up. The absarokas of Wyoming are bulged up. You guys with me? Everything behind it, meaning to the west, is collapsing. Jackson Hole, collapsing. Paradise Valley, collapsing. Okay? It's not being buoyed up any longer by this gigantic bulge of this hot spot. That's gone away, and it collapses. So these mountain ranges started going up when the hot spot got to its present position under Yellowstone National Park. The Tetons are also getting younger as I get older. They're now sitting at about 4.5 to 5 million years of age, which is like nothing geologically. It's yesterday. Okay, I know we're running out of time. Okay, then it erupted, and it sent clouds of hot ash and gas and rock fragments into Montana called pyroclastic flows. This is the Huckleberry Ridge Tuff. We'll see it tomorrow outside of Mammoth. Here it is up close. These are very, very bad days. Then it was glaciated. So the landscape got glaciated starting somewhere about 2 million years ago. The last major ice advance occurred between 19 and 15,000 years ago and started retreating in earnest by certainly 12,000 years ago throughout much of Montana. You can see the ice cover. There was a big ice sheet that came down out of Canada called the Laurentide Ice Sheet out onto the plains, backing up numerous lakes. We get pretty focused on Glacial Lake Missoula, but boy, there were a bunch of really cool glacial lakes out across the High Line that we kind of ignore. And then you have Glacial Lake Missoula that was backed up by the Cordillera ice lobe that came down into Idaho. Okay, we're now into modern surface. Roaming around on that modern surface were animals like Columbian mammoths. We know that they were that humans were interacting with them because we can see the cut marks and so on the bones from that interaction. And it sculpted the landscape into, these glacial horns and scoured out lake bowls and so on that make really the beautiful topography that we enjoy in western Montana. So humans arrived at least 14,000 years ago, and that number is getting pushed further and further back. We've got the site down in New Mexico that's now at 22 or whatever thousand years. So First Peoples have been here for a long time, and they really use the geology. This is one of my favorites. Dylan is down here. This is that folded and thrust belt area. This is a fold. You can see rocks tilted this way, and they go underground, and they come up over here like this. You guys with me? And that downfold created a natural funnel, and there's a buffalo jump right here at the end. So they were coming in here, sneaking through here. The bison are grazing around here, and they ran them down through this, off the end, and then they would process them. This is the Big Hole River, and their encampments were all along the Big Hole River as they were processing them. This is a world-class archaeological site. Very few people know about it, thank goodness. I'm not telling you exactly where it is. Then the metal miners show up, right? In the 1860s, it starts with placer, right? People wandering around the hills, panning for gold. They see color. They then notice the rocks that have orange color in them to look for the lode deposits. What's that orange? Oxidized iron, right. So they know they're metals, right? So these are not geologists, right? I mean, I don't mean this disrespectfully, but these are draft dodgers from the Confederacy. And they found all this stuff. They figured out orange means metal and started digging holes. You go to Southwest Montana, there's a little pick and shovel operation hole everywhere you look. If there was any color at all in that rock, they dug into it and looked. It's incredible. And of course, the big placer deposits, the most famous, of course, the big placer deposit in Alder Gulch, Virginia City, right? World's largest placer gold deposit, period, end of story. By the way, it paid for Harvard University. Harvard was deeply invested in the gold in Alder Gulch. All right, this is Elkhorn, hard rock mining. You can see some effluent. I'm almost there. Okay, then, modern recorded earthquakes. Where are they happening? They're happening on these active extensional faults. So as we're creating basin and range and the valleys are dropping, the ranges are going up, those are the things that hold potential energy, hold, and then boom, right? They release kinetic energy, and that's in the form of a wave, and you feel that as an earthquake. Think of it this way. Butte, Montana. So, Our Lady is rising into the heavens. Butte is dropping into the pits of hell along the continental fault. An active extensional fault, a part of the Basin Range, no different than the faults that are dropping in your Paradise Valley, or the Bridger Fault that's dropping the Gallatin, okay? Or the many of them in my area that are dropping the valley. If it happens in Butte, and I'll deny I said this even though it's on film, it will pop. I mean, they're practically digging the bloody thing out right underneath the interstate. I cannot believe how close to the interstate they are getting with the mining. It is amazing. You gotta love it. Only in Butte. It's just such a classic Butte thing. So they're digging away, and they're right on the fault. And I've been in the pit with the geologist, and she's like, "There's the fault." And I'm like, "Oh my God, they're blasting in here." There's the fault. It probably doesn't affect it, but it plays well with students. And so if it pops and it produces a 7.5 mag earthquake, sitting above the city is the Yankee Doodle tailings pile. A pile that started accumulating mine waste so far back that nobody even knows what's under it. And you can be certain very little of it was engineered as fill. Okay? So then it's full of water. And you pop a 7.5 magnitude earthquake and it shakes like crazy. And it slurries. And down the hill it goes. And what does it encounter? The Berkeley pit. And it hits the Berkeley pit at supersonic speeds. I'm now exaggerating. And it hits the water, and it creates the mother of all tsunami waves of acid mine water. And out of the pit it comes, and it washes like a Catholic event across uptown Butte, stripping the surface of humanity. I can see it. I can see it, but I never say this in Butte. And I've given a zillion talks in Butte, and you do not say this. The other one that gets me is the Mission Range is going up the same way. And at the top of the Mission Range above Big Fork, are tension cracks. It is coming apart. Now, if it comes apart like Quake Lake did in '59, and it comes down and catches air, it'll hit the lake and it'll push a tsunami wave that'll go wash over Polson. I said it first. Okay, so in Dillon we had one in 2005, and so the potential energy built up, and here, and boom, it released it as kinetic energy. And if it's big enough, which means about 6.5, it actually creates a scarp, which is vertical offset of the ground. That takes about a 6.5 or higher. Look at this one from Quake Lake in 1959. There's a person for scale, right? I lost my person. There. Isn't that amazing? Okay, 7.5 mag quake. That is possible on every one of these extensional faults. We have a problem. And nobody really knows about it. We don't pay attention to this. We're building all over these faults. All over the place. I mean, Missoula. Mount Sentinel and Mount Jumbo are going up and the valley is dropping down on one of these faults that could crack a 7.5 mag earthquake. Sitting right there is the University of Montana. In 2 years as a graduate student, I never heard anyone once say that. But it's the truth. That fault could crack a 7.5 mag earthquake. It's active. Like the Mission Fault, like the Bridger Fault, like the faults we'll see tomorrow. Okay? We have a very high seismic risk in Montana, but there's 1 million of us, so we don't get a lot of attention. We have one state seismologist, one earthquake guy, Mike Stickney. Now, he's great, but he's alone. Oh, I have to point this out. Only in Dillon. The Jenga chimney from the earthquake in 2005, okay? That's there. It's still like this to this day. Only in Dillon, right? They're like, it's standing. What's the problem? I'm like, well, because maybe a child walks by and it gets killed? No, I swear to God, it's still like that. Okay, so then hot springs. The hot springs we had, I had to put it in because you guys have Chico. There it is. Look at that. Chico is on a splay of the Deep Creek Fault down along the edge of the Absarcas. And why? Porosity and permeability as they break and move rock. So the water can percolate up and come out onto the surface after it's descended to a depth and been heated by the geothermal gradient of the earth. So it gets hotter as you go down, right? Pressure and the decay of radioactive decay of radioactive minerals and traps heat. So it's hot as you go down. And I mean, the Butte miners, right, working at the 5,000 foot level were in temperatures of like 120 degrees Fahrenheit. That's the geothermal gradient. So as it goes, it descends, it heats up, and then it finds a conduit to the surface, which is always a active extensional fault, always, in southwest Montana. Okay? There's a few wells out in central Montana that bring hot water to the surface, but those are oil wells, they don't count. So this is Elkhorn Hot Springs. This is where it emanates out of the ground. And it's right on the fault. It comes out right on the fault. I mean, look at yours, right? Boom, hot springs. Groundwater. So we have caves, right? How many have been to Lewis and Clark Caverns? Phenomenal place. And so groundwater is actually ancient water. Most of our groundwater got in post-glacial as the ice melted, and we had a wetter climate period in the early, what we call Holocene, we ended up getting a lot of groundwater into in the limestone deposits, like that one full of the little shells of marine creatures, the Madison limestone. And it can travel long distances through these caverns and then come out of the surface. This is Big Springs at Great Falls, and it travels all the way from the Little Belt Mountains to Great Falls. It's been traced, so we know that's what it does. And it follows the whole way. It follows the Madison limestone, and then it hits a conduit to the surface and comes out. Okay? So, we are rich in Montana in subsurface water, groundwater. But it got in there 10,000 years ago. We can date water. And so we know that it got in there 10,000 years ago. That means if we pull it out, it has to be replaced. Well, the climate now is way drier when the water got in there, right? So what are we doing to the water that's in the ground? We're mining it. We are mining groundwater. We are taking out more than is going back in. Okay? Central Valley of California did this. The San Joaquin Valley, the southern end of the valley, dropped 27 feet because the water was extracted and all the pore spaces collapsed and the ground sunk 27 feet. Phoenix, same thing. Okay? We are not immune to this. We just only have 1 million people. But don't believe me? Think about pivots. So in the Dillon area, there's the mother of all pivots. And this pivot is really pulling tons of water out, and it pulls all the groundwater down, so all the wells surrounding that pivot well, they all go dry, right? Because it's drawn down to the big well, Kona Depression. When he's done with that pivot and he shuts it off, what time of year is that? Okay. Is there a lot of moisture at that time of year? Not really. When he shuts that pivot off, the groundwater goes right back up into those surrounding wells, like in days. That's groundwater. Old. Thousands of years old. Has nothing to do with what's on the surface. What's on the surface is only important to our reservoirs and our rivers. And the rivers are mostly intersects of the groundwater. So when we pull the groundwater down, we pull the rivers down. We have to be careful about this. And we really don't pay attention to any of this. So I threw the water in at the last minute because I feel it's so important now. Okay? Now we're into the Anthropocene. Us. And we have issues we've got to deal with. We have mine waste contamination to clean up. We have faults to recognize and avoid where we build our homes. We have landslides everywhere that we need to recognize, map, and avoid. Big Sky is built on slides. Now, they can afford to lose their homes. I can't. So I want to know where the landslides are. Why do I care about this? My family lost a house to a landslide when I was about 7. We never recovered from it. My parents got divorced. I mean, I don't want to give you the sad story here, but my parents got divorced. Money that was going to go to college wasn't there. I had to go to the local community college. We called it UCLA, University of California, by the Livermore Airport. There are consequences, right, to a bad decision. They built on a landslide. They weren't stupid people, my parents. They were ignorant to this geological reality. Why? There was nobody to tell them. There was no rule that said they had to be told. Montana, Smith & Wesson laws. I'll put my house where I please, and you'll pry it out of my cold, dead hand before you'll tell me otherwise. I mean, people are building on floodplains. Don't tell me that there are rules regarding building on floodplains. I'm seeing it violated all the time. People build on landslides. People build on earthquakes or faults. Ask John. We struggle because we see this and we have to drive around. We're like, oh, oh. The worst one is building under the damn sandstone ridges and the rims and Billings. My God, blocks come calving off of there, taking out houses on a time scale that I can relate to, and they still do it. And they're building on top of it as well. So what's the point? The point is at least let people know that these things are, an issue so that families like mine that couldn't afford to lose everything that they invested, their entire lives were invested in that home, and it was lost. And so these can be devastating, lifelong devastating things. And as a geologist, I feel that I have an obligation to help people to avoid them. And so I teach young people in the college classes by showing them in the field what to avoid. A big one is flash floods and alluvial fans. We are building all over the place at the mouths of canyons that can every once in a while be flooded by 10 feet of water and muck and rock. Bannock, the territorial capital of Montana Territory, has been flooded 4 times since they built that city, or whatever you want to call it. From Grasshopper Creek? No. From a little teeny drainage that it is made an alluvial fan that comes into the town. That sucker is lit up 4 times since 1862. And you can't believe the depth 10, 15 feet of water went through Bannock the last time it happened. It happened a week before Bannock Days. Had it happened during Bannock Days, there would have been hundreds of people killed. Okay? All right, so what's our future? Climate. Montana's about water. And this is Maverick Mountain, and I've skied there for 32 years, and I love it. And it is the miner's canary of ski areas. Every year, it's like, is he going to get open? Is he going to get open? January, is he going to get open? Mid-January, is he going to get open? February, is he going to get open? It gets worse every year. Snow's coming later. Temperatures are warmer. He'll get snow, and then, warm storm comes in, it's gone. There used to be a ski area out of Butte, Beef Trail. Not there anymore. Discovery's another one that's on the edge. They barely make it. Red Lodge Mountain, not great. On the edge. This one's the worst. Maverick's the worst. So, what's the evidence for this? Well, because people are skeptical. Fine. What's the evidence? See this blue line? If you take humans out of the equation and run the models, we actually were cooling. Why? Because the Earth is moving slightly away from the sun. The Earth has these variations in its orbit around the sun. And those variations put us closer to the sun, warming us up, putting us further away from the sun, cooling us down. And they occur at different time scales because of different mechanisms going on that's changed the distance of the Earth and the sun. And we are presently in a tiny cycle that is moving the Earth away from the sun. And so we should be cooling off. And the black line is the observation, and it's exactly what the model predicts with human beings and their activities involved, which is warming. Climate is warming. Human beings are responsible for it. It is not an orbital cycle. That cycle is cooling the planet. It's we who are warming it. Now, I'm just saying it for a fact of what it is. What we do about it in terms of policy, above my pay grade. That's above my pay grade. That's a political issue that I have no idea how you do anything about that. I am a sinner. I drove over here in an expedition, a Ford Expedition, by myself. So who am I to point a finger? But it doesn't take away from the fact. So we're going to have to grapple with this. What will ranching look like 100 years from now? That worries me. What will fishing look like 100 years from now? That worries me. What will that groundwater supply that I said is vulnerable to being mined, what's that going to look like 100 years from now? That worries me. What is humanity going to be doing in Montana, which is looking more and more like northern Nevada by the end of this century? Climatically. Okay, not to mention all the other issues that, we now have smoke season, right? Which is horrible. So I don't know. But what I know is tomorrow we're going to go out and we're going to leave this place and we're going to explore this place, and it's going to be a hell of a lot more fun than listening to me yammer on, because that's where the geology is. So with that, thank you very much.